I will be talking about the results of this experiment that we did in Madagascar. I have to point out that, well, as usual, I didn't do the work. The work was mostly done by these people marked in red, which are 2 PhD students, Miriam Rice in Frankfurt and Jennifer Dreiling at GFZ, at my institution. And then Elisa Rindra-Hariasona is a former colleague of Rantos at the IOGA in Madagascar, who has been spending, I guess, in total now 3 years at GFZ with a Humboldt Fellowship, which is a German organization that pays for foreign postdocs to come to Germany. And she has also been working with the data. And, well, I'm the one who summarized it today. I should also say that this was really original in Geotalk, so quite compressed. I have added a few slides, but essentially it's still in Geotalk, so it's quite short on exposition and explaining the background. So I hope you can follow, and I will try to talk a little bit more when I did at AGU to hopefully clarify things. And it's a small informal seminar, so feel free to interrupt. I think we have a time for that. Okay, so let's get started. So yeah, essentially it's structured according to the 3 papers after an introduction. So first is Elisa's work on the isotropic crustal structure. And then we looked at 2 different types of anisotropy, radial anisotropy, which is the difference between horizontal and vertical propagating waves, and then azimuthal anisotropy, from north to east, essentially how it varies. And then some more preliminary stuff right at the end. Okay, so you probably all, or there's certainly people in the audience who are much more familiar with that than I myself, but Madagascar is interesting because it was at this sort of lynch point of assembly of, at the assembly of Gondwanaland was the center of a continental collision zone. That was sort of the first major event affecting it. Then later it underwent several rifting episodes. There was an abandoned rifting episode, which is related to the Karoo rifting here in South Africa. And then eventually it separated, the time sequence shown here, separated to the south along a transform fault really from East Africa. And then finally, as the latest major event is the separation from India, Seychelles at 90 million years, which is probably related to the impingement of a plume. And we we're interested if you can see evidences of these processes in the crustal structure or any communal element to that. Okay, there's also some more recent activity, new gene activity. I'm not really going to talk about that. That affects maybe mostly the north. And our array is essentially, here you see Madagascar, is going from west to east through Madagascar. That is largely, well, it is convenient because it really crosses all the geologic territories, but it's also governed by logistics because Madagascar is relatively difficult to get around in, and there is a major road going, well, basically parallel to, our array is going parallel to this array, and if one wants 10 stations, so the station spacing here is 17 kilometers, it's essentially almost impossible to do it in any other place in Madagascar, well, in the east-west direction, except there. So again, the overall structure is Madagascar is roughly, the western thirds are sedimentary basins of various ages. And then east of that line, roughly the eastern 2/3, it's a Precambrian basement of Archean and Proterozoic age. And then a feature that is also very famous for are these shear zones. These are these green lines here that cut across the Proterozoic domain. Sometimes they seem to be separating here various domains, but sometimes they also just cut across, that are related to these collision processes that are formed, mostly ductile shear zones. Okay, and that the data set we're using is mostly this joint experiment between GFZ and the IOGA in Madagascar. Is this line here. These are the blue stations. We had some short period stations supplementing them. These are these yellow stations, which already required quite adventurous trips off the main road. And then we also used some, at the same time, there's some other groups active. You probably heard of the Macomo experiment from the US groups that had stations all over Madagascar, and we used essentially stations in the south from that data set. And then Guillaume Barrois, essentially, French groups from Réunion, they put some stations along the east coast as part of a much larger experiment looking at the Indian Ocean, and if that is run, we had also had access to these stations. Okay, so the one thing that we did is looking at receiver functions. So receiver functions essentially use teleseismic arrivals from earthquakes far away to isolate the response, the seismic response of, in this case, the crust directly below stations. And what you see here is kind of a compilation of the data. You obviously don't need to understand the slide in detail, but just to give an impression. So for each station, we stack up the results from all the events, and this is what is shown here. And you can see at first glance that they're ordered by the different geological provinces in which they are. So these ones here are the sediments. Well, these ones are the younger sediments, these ones are the older sediments, and then here with various Proterozoic and Archean provinces. And I'm going to zoom in a little bit more so I can highlight some features. So one thing I think that's quite striking is that they're really, even at this level of seismic waveforms, you see quite different signatures. So maybe the most classic crust is here the Proterozoic crust that has a very strong, this bump here is conversion of a P wave to the S wave at the Moho. And that is here very distinct, so that means there's a very sharp contrast at the Moho. And there's only very little energy coming from the mid-crust, so this part here. So there's maybe a little bump here, so it's got a relatively suppressed upper crust, lower crust boundary. Okay, then these things here later, these are multiples, so where the P wave comes, gets converted to an S wave, and then bounces various times between the surface and the Moho. Okay, and they can just give us further hints. So now if we compare this to the Archean domain, we can still see the Moho reflection, Moho conversion, here marked with a red line, but it's a little bit less strong than here in the Proterozoic domain, so the contrast here on average is a little bit less. And we now see quite a strong conversion also from the mid-crust. Yeah, this is this line marked here with the dotted line, the black dotted line. Okay, and then if you compare to the sediments are always very troublesome for receiver functions because they rely on the horizontal components and they tend to be relatively poor in sedimentary basins. But one sees here a very strong spike, which is even stronger than this direct arrival. So the one at 0.0 seconds is always a direct arrival. You see an even stronger one at most of these stations, and that's a contrast between the sediments and the basement. Okay, and that's the strongest contrast. And that has its own multiples, and they tend to come at a similar time as the Moho. The Moho is still marked here by this red line. Here we couldn't really distinguish this from the sediment multiples, but if we look at the multiples, we also see kind of a reasonably strong bump here at least some of these stations, and we later do some waveform modeling, so we're reasonably confident that this is Moho, so we can still identify it even for what's normally difficult to do for these sediments, but it is, I mean, the timing here is much shorter than the timing here between the direct arrivals, so we have a thin crust, as is not really surprising. Okay, there's a technique which is called H-kappa stacking, which I won't really explain now, which allows to derive Moho depth and VP-VS ratio based on the timing of these Moho conversions and then the multiples. And that's summarized here. So we see a very clear pattern in the Moho. So we go from Moho depths of 24 kilometers, so that's basement plus sediment, to then 40 kilometers or so beneath Archean, with slightly less crustal thickness in the Proterozoic domain. Okay, and then for VP-VS ratio, that tends to be a little bit trickier to measure, but that tells us something on the average composition of a crust. It tends to be high here in the sediments, and I'll get to that in a little bit more detail later, and then sort of values of around 1.8, 1.84, and then it's still high in the Proterozoic, a little bit less, becomes quite low in the Archean, so here 1.75, 7.2, and then very high against here in this eastern part. This is something that the very eastern part is something that is influenced by the Cretaceous volcanics on the surface, and there are also various spots here and here that had these volcanic intrusions. Okay, and really I'm showing this because it shows quite nicely the correspondence of the measurements with the various provinces. So really here we see this transition from yellow colors to green colors that is more or less quite well coinciding with this boundary line. And it's particularly striking here, even though this is just a narrow sliver. Here we get these very high values, and then as we change into the province, we go to the low values of here, 1.7, 1.72. So I think that really shows that there is quite a good correspondence of surface geology and total average crustal structure. These are really crustal average VPVS ratios. And looking at all the measurements together and modeling the crust very simply as just sediments, upper crust, lower crust, one can derive, or one can have an idea that these average crustal values are based on averaging constant upper crust, lower crust, and sediment values. And one can explain this, for example, with these values around 1.8 in the west here, by sedimentary VPVS of 1.9 and a more typical crustal VPVS of 1.75. So that's average crust composition. The lower the VPVS ratio in the crust, the more felsic the crust is. Okay, so one can also look at profiles. So what is shown here is essentially what I showed before, these individual receiver functions now turned into colors and placed next to each other. It's not quite that. This one really takes into account where the conversions happen. And essentially where there's a red line here, it means it's a contrast going from a slower to a faster velocity. So in this case here, it's a moho. You also see here the strong contrast from a sediment basement. And the black line is simply the highest sort of conversion, while the green line shows the results of that technique that I described before, VPVS stacking. And this is mainly supposed to show that they agree. So we see again what I said before, that in the west we've got the very thin crust thickening to the east, but then also right going towards the coast in the east we get a quite severe crustal thinning. Okay, and what gives us extra confidence is if we look at the multiples. So now we migrate the multiples to depth, and if everything agrees, that should be at the same depth. And indeed, we see here it's a little bit more diffuse because there's some technical issues arrived at, but we see this red line here, which more or less agrees with that, and even the second multiple, again, sort of it becomes even more diffuse, but there is a peak of a red color where we pick the moho in the other conversions. Okay, and this is kind of a summary figure for that part of the study. So here you see again what I showed before, the moho depth in blue and the VPVS ratios in red from the H-kappa stacking from this particular technique. And then an additional piece of information that in here that I skipped all the details of is the propagation of surface waves across the array. Oh, got an exciting meteorological situation. What these receiver functions are very sensitive to are contrasts in the seismic structure. So let's see if there's a sharp contrast, but they're very poor at really getting the average velocities out. So there's always, just looking at this, there's a trade-off between the velocity and the depth of some interface. And one can mitigate this by looking at surface waves, which are sensitive to the average structure, but they're not really sensitive to if it's a gradual transition or a sharp transition. Okay? And by combining both, we can sort of get the best of both worlds and get a velocity model out of a crust and also information on where the interfaces are. And this is basically done here. So we see the sediments as the very slow velocities up to 3. These are shear bed velocities. Okay, and the sediments are going up to depth of around 9 kilometers, 9-10 kilometers in the west, and then gradually thinning to the east. And as we're gradually thinning, as one would expect from isostasy, the crust is getting a bit thicker. Okay, but then we also see, even for the elevation on top here, we can see it's a bit hard to read, but this line here is elevation. And then in blue is the computed Bouguer anomaly for that model based on some density-velocity relations. And then in the sort of dark green here is the measured anomaly. And in the center of the profile, these match quite well. At the edges, they grow apart, but this is not surprising because we don't really know what the structure is to the west and to the east, so that it's just being ignored. And so there are edge effects because the gravity here is still sensitive, obviously, to the structure here. Yeah, so if you look at the part where it's really where the forward modeling can be expected to work well, it looks okay. So it's another way to gain confidence in this model that it also fits gravity. And it's more or less an isostatic balance. So where the crust is thick, the topography is high, as one would expect. Okay, so now looking in a little bit more detail at the structure here. Well, starting in the west, the velocities are really quite low, so they're similar to the upper crustal velocities in the eastern part. So it looks like the lower crust here was removed by some process, either by being sheared away along a large detachment fault or by delaminating at some stage. There's also differences between the Proterozoic and the Archean provinces, in that the Archean provinces have this relatively fast lowermost crust. And that's the reason why before we could only see the Moho conversion as relatively weak, because here we have got the sharp contrast in velocity. They're going from green to, it's not quite visible in color base, but going from green to blue very quickly. Yeah, so we create a strong conversion. And here we have got a layer that's also very fast, so the contrast is smaller, and we see that more. And conversely, for the mid crust here, the velocities in the lower crust are higher in the Archean than in the Proterozoic, so that this mid-crustal conversion is more pronounced in this part here. Yeah, it's shown a little bit with these dotted lines. Okay, so this is the opposite as was sort of observed by these very old papers of Raymond and Walter Mooney, where the opposite pattern was visibly observed, that the Proterozoic tended to be thicker and have this underplate. I mean, one can come up with different scenarios related to the collision process, why this might have arisen, if that was delaminated maybe, there's some underplate that was here in the collision process, or yeah, there were some later process also related to collision where one creates some new underplate. So that we leave to geologists in a way to speculate on that. Yeah, and then in the volcanics, we have got these strongly elevated VPVS ratios, presumably related to some intrusions into the crust there. Okay, one can also do, this is kind of, I mean, was the summary figure for that first part. One can also look at studies from other parts. So this is really the results that were based on our experiment. And then from the literature, Elisa made a compilation of what it looked like in the other parts that were attached to it during the Gondwana land time. And overall, the crustal structures are, well, there's some similarities, but whether underplating is present or not, it really differs. And also the thickness of the underplate differs also between these different areas. This may be not too surprising, as like in the collision zone, if one thinks of Himalaya, Tibet now, for example, there are different zones that undergo different processes. You can't expect the whole Himalaya, Tibet area to look the same, and so the same with Madagascar and the adjacent Gondwana land regions is not necessarily the same. Of course, also these have been derived by different authors with slightly different codes, so one should probably do a more quantitative comparison at some later stage. Okay, so the radial anisotropy structure, just very quickly as introduction, we measure that with Rayleigh wave and Love waves, and they're both Rayleigh waves are sensitive to both the P wave structure and the shear wave structure, but the shear wave structure has more influence, and it's what is called the vertical shear wave, so that is where the vibration is in a plane that involves the vertical. Okay, and then the other type of this was a Rayleigh wave, yeah, and the motion is, if one thinks the earthquake is somewhere on the left, the motion is basically within the plane of the board here. Okay, and then for the Love wave, the motion is in and out of the board, and that's called the horizontal shear wave. Okay, because the vibration is really just purely on the horizontal plane. There's no vertical component. And if there's a difference between these two types of shear waves in the velocity, one can measure that from the inferred structures from these two types of surface waves. Okay, there's various mechanisms by which one can generate seismic anisotropy. One is so-called SPO, shape preferred orientation, and this is essentially how to build anisotropy from completely isotropic, from mineralogy, isotropic materials, just by heterogeneity that is preferentially oriented. As long as this heterogeneity is much smaller than the wavelength, the wavelength, are not going to see the details of the structure, but they're just the average velocities that differ in different directions. And this can be done by layering, sedimentary layering, or due to volcanic silts or dikes, or by little fractures, also inclusions. And one can very easily imagine that. If you imagine this is a block and these black parts are, for example, steel, and these white parts are some sort of soft material, and if you try to compress that in that direction, it's very easy. Okay, but if you try to compress it in and out of a board, it would be very difficult to compress it. Okay, and essentially the strength relates to velocity, so it's very easy to understand this even without any mathematics. Okay, and this is a mechanism that's, it's obviously in sedimentary basins, for example, and gets the horizontal layering, but it's particularly important in relatively shallow layers, because the deeper you go, the more the pressure will just close fractures. Okay, something like volcanic intrusions that can happen at any crustal depth, really. The other main mechanism is so-called crystal preferred orientation. They're really, so if one looks at single crystals of, for example, micas or amphibole or so, most of them tend to be quite anisotropic. If you have done geology course, you know optical anisotropy, but it's also true for elastic properties. And that doesn't mean, because minerals are obviously much smaller than the seismic wavelength, that their overall structure is anisotropic. If they're randomly oriented, we still end up with something isotropic. And this is why seismology can usually get away with assuming things are isotropic. But under certain conditions, if a piece of rock is subjected to strain, these minerals will all align in a particular direction. And then the whole rock or the whole crust can become anisotropic, and that's called crystal preferred orientation. That is the mechanism that is most important in the mid and lower crust, also in the mantle. But in this talk, in the first part, we're only concerned about the crust. Then on the anisotropy, we'll talk about the mantle. Okay, and just to give you a flavor of the kind of measurement methodology, is we're using ambient noise. So by stacking ambient noise for a long time, one can recover the Green's function, so the kind of the same seismogram almost as one would obtain if one had a source at one of the stations and a receiver at the other station. Okay, and then what is shown here is the cross correlations averaged over a whole year, or averaged over time of experiment between one particular station, which we've called MS09, which is special because it's at the edge between the sedimentary basin and the Precambrian parts of Madagascar. And so going to the north, we're essentially going into the Precambrian part, or going to the east, sorry. And here going to the west, we're going to the sediments. And one can see, if one has a keen eye, that the propagation here, particularly for faster waves, is a little bit slower. Okay, because in the sediments, waves propagate more slowly. So this angle here is a little bit larger than here. And one can do this for both a Rayleigh wave from the vertical component and for the Love wave from a transverse component. Yeah, this is the difference between top and bottom. And well, it's really a bit hard to see, but the Love wave tends to be a little bit faster, so it's a little bit close. I mean, yeah, you can sort of just see it maybe, but these guidelines here, so you see this one is a little bit closer to the guideline than this one here. So Love waves, they always tend to propagate a bit faster. That doesn't necessarily mean it's anisotropic, that's just a property of the waves, but we'll later invert this for seismic anisotropy. Okay, then from these curves, we measure the phase and group dispersions, and this is shown here for the different parts. So the colorful ones are the parts that are purely contained in one geologic province, and the major difference is between the sediments here, the yellow colors, and the Precambrian parts, and then there are also some more subtle but still resolvable difference, say, between here the Proterozoic and the Archean, the blue and the green lines. Okay, so again one sees different crustal structure even in the raw data. Okay, so we take these, the gray ones are just ones that mix different provinces. So taking all of these together, then we can use tomography to derive maps, and again the first order feature you see are the sediments in the west, and then like these somewhat more subtle differences between the Proterozoic and Archean parts. Okay, here it's kind of hard to resolve volcanic provinces because there's such a thin sliver, and surface waves always average also horizontally over some area. Okay, and then one defines this parameter. So, and then at each grid point, one can take these, or looking at the different periods, one can construct a sort of pseudo dispersion curve for each point. It's shown here, and then invert this for a 1D model. And then comparing the 1D models for the Rayleigh and the love wave, if they disagree, that basically is a sign for radial anisotropy. Okay, this is what we've done here. This is shown here, and then the result of it is essentially here. So these dashed lines are just for orientation. They're not derived from that data set, but they're derived from what I shown earlier on the isotropic crustal structure. So this is well, the boundary between the mid-crust and the lower crust is this line here. This is the sediment basin boundary, and this one between upper crust and mid-crust. And then the moor is only seen here in the west, going down. Okay, this one here is similar to what you've seen before, but it doesn't include information from receiver function. So it's just for orientation, really. And the new result is here, that shows the anisotropy, where red colors show that the horizontal shear wave is faster than the vertical shear wave, which you get, I mean, this is symbolized here, you would get from horizontal layering, for example. Yeah? But also, if minerals are, if a strain is such that there is horizontal shearing. And the blue colors show if either you've got vertically oriented structures or there's shearing that's in that direction. Okay, and the first real surprising result, just see how I talk through this, yeah. So this is just the same thing as before, just for orientation, and then here's some interpretive cartoon. So yeah, one thing that's relatively easy to explain is why we've got positive anisotropy in the basement and the deeper sedimentary layers. I mean, the sediments, one would expect by default positive anisotropy, so red colors because of a layering. But also if there's, I mean, to make the basin, you have to shear like this essentially during the crustal stretching phase. So that one ends up, if the CPO is dominant with these horizontal structures, here it makes sense. What was surprising is that we have this near surface negative. Yeah, this is, okay, it's just showing the sequence. So as we stretch it, we create the anisotropy. Okay, what is surprising is the negative anisotropy in the near surface. And I really didn't believe this result for a long time, and I made Jennifer do a lot of tests to make sure it's really true, but in the end she convinced me that really the data demand this negative anisotropy in the top 5 kilometers or so. And it's quite strong. I mean, move the scale, but it's several percent, so it's really a bit, I mean, there have been some other observations of negative anisotropy in sedimentary basins, and usually vertical fracturing was involved, or was invoked to explain this. I don't think this works here because it's simply too strong for a few cracks in the near surface to cause such strong anisotropy to large depths. So one thing that came up, it's not fully convincing, yeah, but this is the best we could come up with, is if there are dike intrusions, we have some intrusions visible at the surface, but not pervasive, but if there are some that go in but don't reach the surface, they would create a very strong contrast and therefore create this negative anisotropy, yeah, because of the vertical structures. And then in the deeper part, they would obviously still go through, but then the contrast would be weaker because the sediment is more compressed, so the other mechanism of the layering kind of wins. And so I would say, you know, it would need further evidence to corroborate that. It's not a super solid conclusion, but it's a more speculative one. Is volcanic intrusions might be even more widespread than suggested by the outcrops. I mean, it's the best way. It's a surprising observation. I would still say it's, yeah, it is still very surprising, but that's the best interpretation we have come up with. Okay, looking at the Precambrian part, one sees mostly the, or at this transition here, one sees also negative anisotropy in the near surface, while further east it is positive. And this coincides with an area that there, I mean, this is more for illustration, but there are some quite spectacular folds. So again, like vertical means potentially some vertical shearing also. And so this coincidence of folds suggests that this is what has happened there. While then in the other part, also there will be a fossil structure from the Pan-African orogeny. And yeah, and then the deeper part, we've got essentially, I mean, if you look at what's happening in Tibet, Himalaya, Tibet now, we get first the compression, but then also we get the gravitational spreading once a certain topography has been built up, and then, so that's thin collisionals, if you so want, and then of course also once the collision stops, when we'll get post-collisional gravitational spreading. And there we would get horizontal shearing in the steeper parts, and potentially also here. Well, these negative anisotropies, again, they're probably some fossil structure from the collision phase that is preserved. The question why this would be preserved and the other ones would sort of be reset in the horizontal spreading is, I would say, somewhat an open question. Maybe also something to do with mineralogy, as different minerals are dominant at different depth layers. But even talking to geologists, we didn't get a sort of a very clear story what could be controlling that. Okay, for the last part of the talk, this is also about anisotropy, but now azimuthal anisotropy, and it's done with a very different measurement method, which is shear wave splitting. So what one does, one takes events that are quite far away and that have waves that go, well, first propagate as a shear wave from the event, then get converted to a P wave going through the core, and then coming out as a shear wave again. And this process of going through the Earth's core, because the Earth's core doesn't, it cannot propagate shear waves, it works like a polarization filter. So we know definitely the polarization of a wave. So shear waves can be, I mean, there's different options. They can have SH or SV dominant polarization, but once they go through the core, they're purely SV polarized. And that means that then, this is again, I mean, all these people who've done a year 1 geology course, you've probably looked at, calcium, which has got this optical birefringence, where you get a split image. Something similar happens with seismology. So we get a fast shear wave and a slow shear wave. And one can measure the delay times between these two types of shear waves. Okay, and then looking at how this varies with the angle, one can figure out a fast direction now between north and east. And this is showing the results of the study here. So going along the profile. What the length of the arrow symbolizes is the splitting delay. Okay, this is hard to read, but the length, like this length shown here, is the splitting of 1 second. So we're all, which you also see down here. Okay, so splitting delay times in the west are very little, and in the east they're around 1 second. And the directions, there are some in the west here. Here's a good measurement again. They're northeast, southwest, here also, and then in the east, but then in the central part they're disturbed and they're northwest, southeast. And roughly, if one looks at where the area where this is happening, it is where there is this area of shear zones. Okay, and these western and eastern ends, the splitting direction is actually parallel to the absolute plate motion. So the direction in which Madagascar moves relative to the deeper mantle, based on the hotspot frame of reference. Okay, and this is something that one observes in many areas. That's thought to be caused by shearing, simple shearing of lithosphere over the asthenosphere. Yeah, and one sets up a horizontal shear layer in the direction of a plate motion. Okay, but it's clearly disturbed here in the part, so we're interested in what causes that, and looking at that, yeah, is there some sort of spatial coincidence with where the shear zones are? Then Miriam did some forward modeling, really a full waveform forward modeling based on the finite difference code. What's shown in blue are the observations, the splitting times here, and the delay times on the top, and then in red what the model would predict. And the first attempt is if you have a narrow shear zone, yeah, so if one can really expect it's so this part here is a crust, more or less, in dark green. This fundamental lithosphere, and then below the asthenosphere. Yeah, so in the asthenosphere here, it's this absolute plate motion direction. Then here's isotropic, and then a narrow shear zone. And you can see that this doesn't fit the data. It disturbs it only over a very narrow area. Another attempt then, if one makes a wide zone with disturbed anisotropy with very sharp corners, and again doesn't fit the data. Okay, we can now fit the fast directions more or less, but the splitting delay times, because of a sharp corner and there's some finite difference effects, where expect to go quite large at the edges, and they don't do that. So that doesn't work. Okay, and that what does work is if we have a shear zone, or we have a similar anisotropy, aligned roughly with the direction of a shear zone, so northwest, southeast, but then some transition region where the splitting is smaller. So it becomes smaller here at the edges. And this one can fit the observations, and here it's all in the crust with relatively strong anisotropy of 12%, but feasible. We can also put it in the mantle lithosphere form. Okay, so which these SKS waves were not really sensitive to at what depth level anisotropy occurs. So the data cannot clearly distinguish between these two cases. Based on geological reasoning, it might be, I mean, it's very likely that there's some anisotropy in the crust, so this model I would say is unlikely on geological grounds, but it could be a combination, so it could be both the crust and the mantle being sheared. So we're really talking about a very wide zone that is being sheared, that's not limited to very narrow shear zones at the surface. Okay, and in the asthenosphere we've simply got the motion, parallel motion, which is really pervasive throughout. Okay, but it gets overprinted by this lithospheric signal in the central part. Okay, so that was the main result in azimuthal anisotropy. And then finally, these are just some preliminary work that's in progress. So before, all the surface waves were done with ambient noise, which limits frequencies to around 25 seconds and most sensitivity to the crustal structure. We've also been looking at earthquakes, which then gives us information about the lithospheric thickness. And we do find lithospheric thicknesses of around 100 kilometers, both using radial and love waves, and indication, the fact that these two pictures don't look the same, shows that there's also radial anisotropy within the lithosphere. Okay, and then this is another way of looking at lithospheric thickness, which uses S-receiver functions, which is similar to what I showed in the beginning, but having S waves, so what I showed in the beginning was P waves that convert to S waves. We can also do it the other way around and look at S waves and then convert to P waves, because the P waves travel faster than S waves, were arrived before. And so looking at precursors of a S phase, one can also look for contrast, and one recovers here the crust as before, and also here this faint blue line, which could be interpreted as a lithosphere-asthenosphere boundary, and it agrees, actually, this is what is shown here. It agrees quite well, except in the west, with what is inferred from the surface waves, which is this kind of blue to green contrast. Something funny is going on in the west. We've also seen this in the peer-receiver functions with these low velocities here in the lithosphere, so that's we still need to figure out, and I hope to talk to Ranto a bit and see if we can use some other technique to look in more detail in that, but that's coming up. Then there's also another part of the study where we look at the seismicity. So this is what was basically known before, which is a catalog from the institute in Antananarivo in Madagascar, where a lot of the seismicity is in the central part and mostly normal faulting. So Madagascar is being pulled apart. There is very little seen in the south. Our array went down here, and the kind of new results, which still has to be checked for some events, is shown here, where we actually do see quite a lot of seismicity in the south, but also somewhat diffuse. But it does seem there's quite some activity. This one is also an area, I have to say, where there's a lot of mining activity, so we still have to do the work of figure out what is actually natural among these events. Okay, and zooming in a bit, yeah, we see these are the better constrained events. Yeah, it just shows again that the seismicity is quite diffuse, but definitely also the southern part of Madagascar is seismically active. Okay, and there was actually, during the deployment time, there was an event here. I think it's probably this one here, right at the end of the line. And this is ongoing work of Ranto's looking at that. So I'll learn a little bit more about this afternoon, I hope. Okay. So, and these are just the conclusions, the main kind of take-home points. So we do think that the crustal structure in anisotropy in southern Madagascar is dominated by these major processes of Pan-African orogeny and the breakoff of Gondwana land. The Archean crust is thicker than the Proterozoic crust due to some kind of underplating. I mean, whether this is because the underplate below the Proterozoic has been removed, or whether it was added to the Archean at some later time. I think it's still an open question. The lower crust was completely lost from the thin basin between the Morondova, below the Morondova. And yeah, the radial anisotropy pattern probably reflects the collapse and thinning in Precambrian and the Morondovan basin also. And we see evidence of a around 150 kilometer wide fossil ductile deformation zone, rather than very focused deformation around the mapped shear zones. So involving not just where we see the shear zones at the surface, but everything really. Okay, thank you very much.
Thank you. Any question?
So, do you see any evidence for seismic with fast keel on the Archean portion?
Not a deep keel. That's in a way what I initially was surprised at. So again, we have a thickness of not more than 100 kilometers or so for the lithosphere. I think it's just because it's a relatively thin sliver of a keel surface. So I think that there might have been some loss of a keel, or just the part is too small to really support a large lithospheric keel. It's more, yeah, I don't think it's a classic craton, right? Because it's just this thin part. It's probably more something like a belt or so.
Further north in the center of Madagascar, there's been some quite recent volcanism. How do you, I know it's outside your profile, but have you got any thoughts on where that comes from?
The US team have been focusing a little bit more on that, and they see in the mantle large, sort of low shear velocity zones, and they're related to the deeper, these deeper structures, deeper plume structures, coming eventually from the lower shear wave province. This lower shear wave velocity zone in the mantle. Yeah, it's also been showing a lot of uplift, which is again, consistent with that explanation.